session. So this is the Masters in Computer Science Enterprise Software Systems at WIT, and this is the Agile Software Development module. My name is Eamon de Lester. You can find
and I'm Siobhan Drohan. Yeah.
Siobhan there is joining me, and you can find information on me on the website here. I'm a founder member of TSSG, also work in WIT. And Siobhan?
Yeah, so my name is Siobhan Drohan, and I've been a lecturer in WIT for about 14 years. And I came from industry where I would have done a lot of software development in industry across various different companies. So, hello, welcome. You'll be with us for 12 weeks.
And we're looking forward to this first session. As I mentioned, it is recorded. That means that anything you type in the chat window here is also recorded and will be part of subsequent videos later on. The recordings will go up probably tomorrow sometime, and we will be breaking them up into multiple talks, and I'll talk about that now in a moment. So the plan for today is I'm going to give you a quick overview of our course material here, give you an idea of how it's laid out and likely structure. And then we're going to go through a series of talks this morning, Siobhan and I taking every second turn, to explore a background to the course itself and setting up for the weeks ahead. Let me just talk to you about the course material first. You arrived here possibly through Adobe Connect. I'm highlighting that currently. And this link here is the module home, and this is the current topic we're about to explore today. If we enter into this topic, our videos will be appearing here. There's a short introductory video here. And these are the talks we're going to proceed with this morning. An overview, a general introduction to software paradigms, we're calling it, which is a background to the field in general, an exploration of the evolution of programming languages, and a short case study on programming language convergence. Siobhan and I have prepared and are sharing this material with you this morning. You'll also find in here a lab. We do one lab per week, sometimes two. This is the lab here. And the labs are designed to reinforce the material we cover in class and to build up a set of skills which will be demonstrated by you in the assignments that Siobhan will introduce shortly. I'll briefly review the structure of these labs for a second so you get some idea of how we're going to run this. Each lab is a series of steps, instructions, screenshots, quite practical. First one should be fairly easy, really. And they're generally building up projects that we'll be elaborating on week to week. Each step should take, each lab should take an hour or so, an hour and a half maybe. It will include quite a bit of code fragments. These will be presented and you will be pasting these into the project as you go along. And it concludes with a summary of the lab, the solution to the lab, or rather the project built up during the exercise itself, and some exercises which we feel would be useful. The exercises are largely optional, but they would probably be a considerable aid as you progress through the course. We also have some reference material here, which you can look at in your own time a bit later on. So that's the module home. This is one topic, this morning's topic. Each week there'll be a new topic appearing at this level. If you want to peek ahead, this is what it'll look like after 4 weeks and after 5, 6, and this is the rough approximation of the topics we plan to offer you. We'll be building up to about 13 labs in total, and we'll be building up to a considerable range of talks and other material and resources. Just some information how the session is going to go this morning by handing over to Siobhan now very shortly to do the overview. At the end of each talk, we're going to pop up a little quiz. So just to get an idea of how you're getting on and maybe a little bit about your own background and experience. You needn't bother with taking that quiz there for the moment. And then when we've done the quiz, we've had a little break between each talk, we'll resume with the next talk. So great to have you all here. And I'm going to hand over now to Siobhan first to give you an overview of the course, assessment, schedule, and general expectations we have on the course. See you shortly.
So as soon as Eamon finishes sharing the screen, I'll take over that screen there now, and we can get going on it. Can everybody hear me? So, sorry, just getting set up here. So basically, hello, welcome, and I'm Siobhan Drohan, and I'm going to just go through the an introduction to the module here that we have. So the agenda that we're going to look at is basically introducing us. So Eamon did an introduction there, and we'll have a look more at that. And I'm going to talk to you about the structure of the module. This is the Agile Software Development module, and we'll just go through the structure with you about that and how we're going to plan on troubleshooting labs. That may change as we progress through this module, and we'll see how things are going, but we have an initial plan of how we're going to troubleshoot our labs. I suppose one of the main things that you're going to be wondering is how are we going to assess this, and the great news is we'll tell you all about that today, and then we'll just give you some kind of ethos and links of the module, links that are associated with the module. So these are the links to the profile that Eamon showed you there earlier on, so you can find out about Eamon directly through there. And also our contact details are here as well. So Eamon's details, along with my details here, and a contact email address. So the structure of the module. So we will have 12 weeks of delivery altogether. And as you're aware from logging in, that we're dealing with 2 different time zones. So on Wednesday, what we plan on doing is a lecture between 5 to 7 p.m. Greenwich Mean Time. So that's for those in Ireland. And then 12 to 2 p.m. for those in America. And then our lab times, where we will, when we say that this is when we plan on running it, this is when Eamon or I will be directly available in the chat room that we will talk to you about later on. And we plan on being directly available at those times between 3 and 5 p.m. Irish time and 10 a.m., which calculates at 10 to 12 in America. So what we're going to be doing is we haven't brought you into Moodle yet, and that's our platform of where you access all of our notes. We're going directly from our GitHub repo so that we don't have to get you enrolled properly and so on. So we will probably start using Moodle at some stage, particularly for you submitting your assignments, but we'll guide you through that as well as to what we expect or how to get onto it and so on. Obviously, we're using Adobe Connect for this session here. And GitHub, that's where you will see that all of your notes are hosted on GitHub, that we publish them out there on a weekly basis, and we publish them on a timely basis so that you can have an access to those notes prior to the lecture starting. And Gitter, this is the chat room that we propose to use. At the moment we're using the chat room that's inside an Adobe Connect, but that's only alive when Adobe Connect is alive. So what we're going to do is use Gitter so that we can you can leave messages for us and you can contact each other and so on. So that'll be our central contact area outside of Adobe Connect. And my screen is taking a little while to load there. You just have to bear with it for a second. Okay. There's one slide refusing blankly to show for me. So what we'll do is we'll move on to the next one anyway. So what we're going to do is how we're going to troubleshoot our labs. So basically what we're going to do is, this is the plan at the moment, is to post the issue in Gitter. So that's the chat room that I just introduced you to. And we will show you how to log on at the end of this session. And basically if you post your issue in there, whatever it is, think of it as asking a question in a traditional classroom. And give us a little bit of a hint as well as to where it's happening, things like that. So maybe screenshots, anything that you think might be helpful to diagnose the problem that you're having would be great. And what we do is we will encourage classmates as well to help each other. You're all working on the same lab, so chances are if one person has a problem, somebody else will have encountered it. So maybe if you know the answer, reply to them. We'll reply anyway, but all of our responses will be in Gitter so that all students can see the resolution. So we will keep everything transparent and open so that everyone can see these things, except for obviously private chats. Now you'll notice there that my spelling, I apologize already, you will notice this quite a lot. So private chat is also possible with us in Gitter. All you have to do is just do a private message in Gitter. If your question is of a nature that you don't want the class, the rest of the group to see it, you can email us directly. So at the moment, Eamon and myself, we plan to do the lectures together for the moment, but maybe as we progress through the module, you may just have one lecturer for your lecture session in a particular week. And if that's the case, then email that particular lecturer during that, who is delivering that week. So then we'll have troubleshooting labs outside of the 2-hour session. Now, this is what we're planning on doing, is when we do bring you into Moodle, we've started creating a frequently asked questions section in Moodle, but it is an incredibly embryonic release of it. Only a couple of questions in there, and we anticipate that we will populate that more as the module goes on, or we may abandon it. We'll see how the module goes. But one of the main things when you're outside of the 2-hour session, if you have a particular problem, have a look in the chat room, have a look in Gitter. We will be using Gitter. So have a look in there and see, has the question been asked in there? And if not, maybe it might be on Stack Overflow. Stack Overflow is a great resource if any of you have ever looked at it, and we have the link at the end of these slides. Or some other sort of troubleshooting software, knowledge-based software. Then maybe post, if you can't find the answer from a little bit of kind of investigation, post your issue in the chat room, or you can contact us directly, and we'll be monitoring in and out a little bit of the chat rooms as well, so we'll be monitoring those. So the main thing that you're supposedly all wondering, what's the assessment structure for the module? It's 100% continuous assessment. So that means that you will not have an exam at the end, and we will be focusing on projects. We'll be getting projects from you. So the first assignment is worth 40% of the overall grade for this module, and it's due the end of midterm. We have a slide coming up now which will show you the where that is, where midterm falls in the calendar. And assignment 2, which is 60%, that's due early January. We will be finishing up lectures in around the middle of December, so it'll give you a fair amount of time over the Christmas period to still enjoy Christmas and also produce a project for us. The very last one, the first assignment, we won't be looking for any sort of presentations from you. So what we will do for the second assignment, though, is we'll get you to record a 5-minute presentation or video. We will give you a PowerPoint template as well, so that you have an idea of what it is we're asking for in the presentation. And then we'll probably do private connects through Adobe Connect, where it'll just be yourself and the two of us, myself and Damon, and we'll do maybe a code walkthrough through that. So you will submit your assignments through Moodle. Your assignment Dropbox, you'll see them, they will look like that, and we will introduce you to Moodle in a few weeks, and we will show you where those assignment Dropboxes are. So the ethos of the module, well, I suppose it's a master's module, so I suppose self-directed learning outside of lectures and labs is where we would be going with this. You will see that a lot of times when we have material on the slides, there will be links to it, so we will send you off you can go off and investigate deeper if you fancy. And being inquisitive and motivated as well is handy. Helpful to peers, I suppose that's from the Gitter perspective as well. So kind of we're hoping to build a level of community through Gitter so that you can all support each other as well as us supporting you. And it's very important, the second last point there is engagement and staying current with the module. That is quite important because the lectures will build upon the previous one. And you might find that this might snowball out of control if you don't keep up to date with your lab work and your lecture work. So I suppose missing 1 week and trying to catch up on it later on is grand, but if you start missing a couple of weeks, the module can become a bit of a challenge. So another thing that's important is all the work submitted must be your own. And we will be doing different, that's why we're doing the presentations and so on. However, like all code and approaches that we give you in the module, so you'll see that we will give you solutions, we will give you loads of different approaches of how to attack certain problems. They can be reused and repurposed in your assignment. That's not considered plagiarism. So you can repurpose all materials that we give you, but the work then must be built upon by you. And the slide that didn't display was the plan for the weeks. So what I'm going to do is go back here now and just see, will it display for me? It's still refusing. Is it going to do it? What I'll do is when we take a break, I will put it onto another presentation and I will show it to you straight after the break. I'll show you the assignment, the structure of the module, the 12-week structure, and what topics you can expect to do in each of those 12 weeks. I apologize, it's not showing there. So If you have any questions, you can type questions into the chat room down at the bottom here. And so what I'm going to do then is I'm going to stop sharing and I'm going to put up just a little quiz and give you a 5-minute break. Eamon and I will be available through the chat room. We'll be able to chat with you if you have any questions, but it just gives you time to take a 5-minute break in between. Okay, so thank you for listening. There we go. Hold on. There's the slide. I'll just share it again. Sorry, a second. It didn't like it in full screen mode for some reason. So you can see there's the structure that I was going to go through that refused to display. So what we've done is this date here is the Monday. So the week starting the 18th of September, we're doing paradigms and languages. So that's today. Now what we have done is we've said that we will deliver these individually. We may change our minds and deliver them together. We'll have a look at how today is going and so on. So as we progress through the module, the next 3 weeks, we will focus on Java. So if you're not clear, or if you've never done Java before, but you've strong programming skills and something else, we will be doing a whistle-stop tour for about 3 weeks on Java. So you'll be happy to hear that, I'd say. The assignment 1, we will release the spec to you next week for assignment 1. So you can be working on it as you're progressing through the labs. We will cover then test-driven development, and you can see test-driven development is appearing throughout this module a fair bit. So we will be covering test-driven development with you. And then we will be doing a lot of the agile tool sets, like Maven and so on. We'll be looking at cloud, a lot of different ways of testing and so on. And we will be covering what we call solid principles. We'll do 3 of the solid principles with you behind object-oriented design. So that's the layout, and you can see here the assignment here, midterm. You can see which week it is. It's in between the 2 of those. That's the assignment will be due that Sunday. We'll release definite dates or definite time to you and how to submit it coming closer to the date. And then when you come back straight after midterm, we will release assignment 2 spec to you as well. So that's the structure of the module. And so what I'm going to do is give you the little break that I promised you. And I'm going to set the timer here so that you can see when we're going to start again. I'm going to switch off my mic and my camera, but we'll still be available through the chat room if you want to have a chat with us. So see you in a few minutes.
Okay, guys, welcome back. Thanks for taking part in the poll. Just going to have a quick look at the poll now, and then I'm going to resume our chat this morning. Yeah, we can see it's kind of what we're expecting, really. Small minority or quite a lot of programming. 40% quite a bit, 30% somewhat, and a smaller group with very little. Also a few not at all, which we might have a look at or check in on later. I'm going to share my screen now. I'm going to move on to the next topic. Hopefully you can see this screen appearing now. And we're going to start to explore our first talk, really. That's part of our module proper. I'm going to start with a talk on software paradigms. I'm just going to take down the poll before we proceed any further, and we might look at that poll results again later on. And we'll then get into our first talk proper. Okay, software paradigms. I'm going to talk about 20 minutes or so, and in this talk we're exploring general concepts in software development, and we're also exploring a range of the alternative disciplines within software, some of which we'll be touching on in the course and some of which we'll hardly be mentioning again. This particular talk is quite high level. There may not be a lot you'd follow up on subsequently. It's tended to give you a flavor of our view of the field, really, and organize some of our thoughts prior to plunging into more detail on the topics we proceed with. I'll start with a quote which embodies some of the principles around which we've organized this course here. And this is from quite some time ago, and it's an observation around how we can improve our programming capabilities. In particular, how can we learn good programming skills? And a lot of the learning comes from looking at existing programs. This is why in the course of our work here for the next 12 weeks, we'll be showing you a lot of code. We'll be exploring a lot of code in the labs, and we'll be reviewing code in the slides and in our talks. And we're hoping that through looking at code frequently and illustrating via code the principles we're uncovering, we can inculcate some key important practices and move your understanding of the discipline forward. Our talk this morning is in two kind of parts, really. We're going to talk about software paradigms for a few moments. It's an interesting word to use, and it has some general context and meaning that is quite subtle, and I'd like to just spend a few moments talking about that. I'd also like to look at the stack I'm showing you here, which is, I'm calling it a software engineering knowledge stack. It's quite ephemeral, really, but we'll walk up through this stack, exploring different concepts along the way, and perhaps we'll use that as a foundation to indicate what parts of that stack we're going to be investigating in our module. First of all, let me talk a little bit about software paradigms. Paradigm refers to a kind of a category or a set of entities that share common characteristics. More usefully, we might think of it as a conceptual way of thinking or describing something. It's a general, maybe class of concepts and values, given a name often, which we can recognize and use in conversation and in exploring the discipline further. The notion of a discipline being divided into paradigms is common across software and scientific disciplines. If we're looking at software, you may have heard of some of these terms in your careers to date: imperative programming, declarative programming, object-oriented programming. These could all be paradigms that have arisen in the history of computing. Some of these paradigms are alive and vibrant. Other paradigms are less visible these days and maybe heading towards more sunset type behavior. These paradigms, though, have a certain structure to them. And it's a structure that was uncovered not just in computing, but in science generally. And this is one of the most influential texts in the history of science and the philosophy of science. It's Thomas Kuhn's Structure of Scientific Revolutions, and it was published many years ago, late 50s, early 60s, I think. And he assessed that, particularly in physics, but also in science generally, paradigms arose periodically as the disciplines evolved. And those paradigms centered around communities, and those communities shared beliefs, values, sometimes a symbolic language, and also examples. And those communities became very active and very vibrant, and also they became very influential around various views of a given field. Now, why is that relevant to us? Well, he also coined the term paradigm shift, when one paradigm gives way to another. And it's quite common in science for these shifts to occur periodically. Periods of uncertainty and confusion can abound as a new paradigm takes hold. That new paradigm often represents breakthrough thinking and often represents a community moving from one field to another new way of doing something. And we see this quite periodically in software. In fact, there is a proliferation of paradigms in software. And if we're looking at it from the perspective of programming languages, we find that a given language can support many paradigms. And in fact, these paradigms can in turn overlap and embody a set of concepts that are distributed in different disciplines. Trying to put sense in all this and trying to have an absolute taxonomy of the paradigms and forces is impossible, really. But we do recognize that there are different schools of thought in software development. Those schools of thought are often overlapping and they're often in contention. And we're aware of those paradigms as we explore a discipline over time. For our module, these are the general areas, if we call them paradigms, that we're going to be exploring. Object-oriented programming, particularly principles within OO given the term solid, which are a venerable set of principles to guide the construction of object-oriented programming programs. Our core language is going to be Java, but we're also going to go beyond Java occasionally into successor languages, and that'll be the subject of one of our talks later on this morning, Kotlin being the language of choice. But in parallel with our exploration of OO programming, we're going to be talking about agile methods as a whole, and particular two cornerstones of agile thinking, test-driven development and automated configuration management, or continuous integration is also called. To illustrate these topics and these concepts and, let's say, paradigms, we'll be building little applications. The application is built in Java, and we'll be doing some network programming by ensuring we can have some interesting problems to solve that will ultimately be web applications or web services. I'd like to just take a walk through this knowledge stack I mentioned earlier, just again to set the scene for where we will be, and also to paint a picture of some of the key breakthroughs that have occurred in this field over the years. We'll go from bottom to top, and starting with programming languages. This is the bread and butter of many of your fields, particularly those of you who are programming very frequently. And you're probably adhering to a small number of languages that you've learned. Maybe you're focusing on one language in particular. When you're acquiring a programming language, you acquire an understanding of the syntax and semantics of the language. That is the structure and appearance, and also meaning. But over time, you're also accruing a set of idioms in the programming language. And these idioms are often ways in which you might apply the language in certain contexts. Very often these idioms are not known when the language is invented, and they arise over time and over experience with the language, or over experience with the language as it evolves. In fact, Java is one such language where many of the idioms in use came into use long after the language itself was first coined. Now, the evolution of language is quite fascinating, and Siobhan will be dealing with that in a talk in a few moments. Languages do have heritage, they do have predecessors, and they influence successors. And the range and diversity of languages is quite staggering. This is a drastic simplification here of some of the origins. And many of the languages, as we mentioned, embody paradigms: imperative languages, declarative languages, object-oriented languages. These all are clustered in different zones in this particular diagram here. And Siobhan will be exploring some of that with you a bit later on. Often when we're choosing languages, though, we're not going to the family tree. We're going to what is it we're building. Is it a web application? Are we building a game? Is it analysis? Are we building a mobile app? And languages cluster around these areas. Some general purpose languages can be suited to many of these fields. Others are quite specific and specialized, particularly in data analysis. As a programmer, we're usually keen on seeing, well, which one is popular, which one is rising, which one is falling, which one should I invest my time in, which one could have a positive impact on my career. You'll find a lot of tracking polls on languages out there showing percentage change over year on year, which language is coming, which language is going. Surprisingly, though, if you look back 10 years, the top 10 is reasonably stable. It takes quite a bit of change for a language to break into that top 10 and remain there consistently. Some of these analysis center around Google search terms, and they try to give you a picture of which language is gaining in popularity and which is steady, which might be declining. CPHP here in decline, perhaps not too much of a surprise. Python, very dramatic growth here due to interest in analysis. Java, possibly in relative decline, although you'll find other polls indicating that Java is reasonably stable. JavaScript there, looking like it's steady, although you'll find other polls and surveys indicating that its growth is explosive. Very unscientific field, really, trying to figure out which is the language of choice. But the top 10, certainly top 15, are well known. If I just go up this little stack just to make some observations along the way. Once we've mastered a programming language, we're often, if we're studying programming, our next port of call is data structures and algorithms, or data structures and problems, as I've called it here. We would expect our language to support these now. We wouldn't necessarily be building these from scratch anymore, although there was a time when we did. And of course, we're also expecting our language to maybe have a toolkit of algorithms we can make use of. Common categories of algorithms that are the stock and trade of a programmer's world are searching, sorting, traversal, inserting, deleting into data structure, classification, merging, etc. These are the bread and butter, really, of the programmer. In our lab today, we're going to be doing some very small Java fragments illustrating some of these concepts. For instance, on the right here, we have a data structure, a list, and you'll be using Eclipse to run this program, stop it, explore the program, look at the data structure in real time. In fact, our IDEs are powerful now. They can show multiple views of a data structure. A logical view, which might be the view we would draw on a whiteboard if we were contemplating a list, and also a physical view, which will show considerably more detail as to how the data structure is actually implemented by whatever library we're currently using. And you'll explore both of those today. Still on this knowledge stack, it's going up one more level to design patterns. We consider these to be broader in scope than data structures and algorithms. They're working at a higher level of granularity. They're usually tied to a paradigm. So we talk about paradigms and patterns in an object-oriented context, or maybe functional patterns, which would be quite different. And these patterns aren't libraries. They're not code, really. They are solutions to known problems, particularly problems that are recurring in the field and problems that can be solved with the benefit of insights from previous solutions. It's a fertile area in its own right. Pattern thinking is largely driven by making the solution resilient to change. If the application we're building is a one-off and may never need to be modified subsequently, it's a prototype or disposable, then patterns are less interesting. But if the application survive, particularly survive changing requirements, changing platform, perhaps even changing programming language, then use of patterns could dramatically improve the lifespan and quality of the solution. And patterns themselves are further divided into levels in their own right. At lower level, idioms, so programming idioms and patterns overlap to a certain extent. Indeed, patterns often gravitate towards idioms if they're widely used. We use the term design patterns for mid-level complexity, whereby we're dealing with classes and objects in general and their relationships. And patterns is often applied at a higher level to architectural considerations. Higher level patterns that embody broader approaches to entire systems. These are some examples of higher level patterns that you might encounter: domain, presentation patterns, messaging patterns, message router, pipes and filters, for instance. Here's an example of a pattern, and you'll notice I'm showing you code. It's kind of strange. And this actually is an extract from one of the programs in the lab today. If we're familiar with pattern thinking, we would be able to identify a pattern here fairly quickly. And the pattern would be the use of a static member of a class, and also the use of a static function to access that member. That's the singleton pattern in action. And effectively, we are establishing what you might call the global one-off instance of an object in the Java context. Now, if you're new to Java, that won't make much sense yet. We'll be introducing Java in the next few weeks, and this code itself will be part of our introduction. If you're familiar with another programming language, you might see some echoes in the syntax we're using here, particularly if you're using C# or C++ or C. Some more design pattern examples. We do have another module on design patterns, which we may be offering next term. The patterns we visit in that module are the classic patterns still widely used today. These patterns are given names, and there is a canonical representation of these patterns in many programming languages, including most modern programming languages. So for instance, the pattern we just briefly looked at here is in the catalog as singleton. And you might have heard of other patterns over time. Perhaps you've come across the word command, or perhaps you've seen the word observer used in other contexts. They're the names of patterns with their own literature, their own examples, and their own trade-offs, which perhaps we'd explore in another context. Going up one level, components. Here we're talking about reusable code packaged for interoperability and published in known locations. Component thinking has been very central to the last 10 years of software engineering, particularly ways of making the components independent of acquisition and deployment. We essentially try to package reusable code, particularly reusable code that can be generalized to more than one application, into a component catalog, and hence into more widespread use. In your lab today, we'll download and use a component just for the fun of it. Here is another fragment from the program, one of the applications you will run in the lab. And here's an example here of a component which we will have downloaded. It's a component for turning a Java object into XML. And once we incorporate the component into our application, then we'll be able to reference it in our application and use it subsequently in the creation of objects and ultimately in the production of output, in this instance, an XML version of our data structure. So the IDE we're using understands components. The language we're using has a component packaging standard called jar files, and you'll get some experience of that today. More component definitions. I won't go to these in any detail. You can look them up if you like. Modern component research has moved on to services combined with components and combining very small or fine-grained components as microservices. It's a fertile area of research and also a quite rapidly changing area. Okay, I'll finish off shortly. Just keep on going up this stack. We're going to architectures. This is quite the highest level, maybe, possibly with the exception of frameworks, whereby we can contemplate an entire system or a system of systems. This could have been encountered during pattern thinking, but often we extract it from patterns and look at it more globally. And here we're looking at quite high level approaches to how an application is structured. For instance, a layered system with application, domain, and infrastructure services, or a pipe, ports, and adapter system, whereby the system is parceled into independent units communicating across known specific channels, or service-oriented architecture. You may have come across that, particularly those of you working in a service environment. Here we're not really talking about code. We may not even be talking about a paradigm. We're talking about high-level constraints on a system. And the focus very much is on the information architecture of the enterprise, as opposed to a specific software engineering pattern or technique. This is beyond the scope of our course, this thinking. Lastly, I'll just talk about frameworks. We could have put frameworks below architectures. I'll put them above for the moment. And frameworks, in fact, are within the scope of our work here today, because they're very influential in the styles of development that are most common in the industry, particularly web development and mobile app development. Both fields rely heavily on framework thinking. And without the presence and effective use of frameworks, it's difficult really to make too much progress. Frameworks in this context, we can consider them as large and sophisticated libraries designed to be extended and reused in a variety of contexts. They often embody a design that is complete and is designed to be then extended by the programmer to deliver a working application. We might think of it as a set of classes, perhaps, who already have an embodied relationship, and then our application becomes an extension of those classes, building on the relationships and abstractions in the framework itself, and taking the framework to its conclusion, which would be a working and running application. We'll encounter a framework when we move in to see if we can take our little laboratory experiments onto the web. And we've selected the Play framework as a reasonably easy to learn framework for building web applications. It's in Java and Scala, and we'll migrate some of our earlier labs into Play applications later on. Okay, what are we doing then in this course again? Having toured through this field, let's just summarize it. We're assuming you have a general programming ability. You have computer science in your background. If you did an undergraduate degree in computer science and you had some programming there, maybe you didn't do a lot since. If you didn't, you will still, I think, gain from this course, because our first few weeks will be bringing you up to speed as soon as we can on modern Java, and then pressing on with some experiments and exploration of the principles we're uncovering. Once we've Java out of the way, we're looking at solid principles, as Siobhan has mentioned. We'll be discussing those in more detail in a few weeks. Test-driven development is key to the entire course. Build processes, network programming via our Play framework, and we're also interested in moving beyond Java into successor languages and perhaps competitor languages, which are exhibiting a range of features which we think are important, and we will be touring them in some detail. Okay, that's my chat for the moment. We're going to take a little break now so that you get time to have a break. I'm going to give it perhaps 10 minutes this time. During that time, please feel free to ask us questions either in the Gitter chat room or in the main chat room here. The Gitter chat room, I think people are dropping in already, is available through our course web just by opening this chat here. So you can drop in there and have a chat with us, or if you like, you can continue to talk on the Adobe Connect chat room. I saw someone mention that a Gitter may be blocked in your organization. We can maybe discuss that in the chat room and see is there strategies around it. Okay, thanks for your attention, and we'll take a little break now, and we'll come back in 10 minutes.
Hello all, can you hear me? So welcome back. Perfect, thank you. You can hear me, that's great. So welcome back. So I suppose one of the first things we'll do is just look at the results of the poll here. And so it's a fairly distributed kind of set of skills here. But if you're after ticking lower down in these, don't worry. This is the first couple of weeks are designed to first couple of maybe 3 weeks or so are designed to bring you up to speed in programming, particularly in Java. And so they'd be good weeks to concentrate on. So let me see. I'll just close down this poll and then we can get going on the notes that are there. Okay, so your programming language evolution. So what we're going to do is we're going to look at the family trees that are out there. And Eamon showed you 1 or 2 family trees there, but he didn't go into detail. And what I'm going to do is delve into those trees. And we look at different characteristics of languages and how some languages are classified. And that brings us then into what we call the typing spectrum as to how languages are classified. So Eamon was discussing this diagram with you on the last set of lectures. And he alluded to the fact that the frameworks, when he was talking about the play framework, that framework, you can code in that in Java or Scala. So your choice of framework will dictate what languages that you can actually use in it. And the choice of programming languages will restrict accessibility up these layers up here. So that if I choose a specific language, it will restrict the actual frameworks that I'm allowed to use. So generally what you do is you pick the framework based on what it is you're developing, and that will dictate the language that you're going to use. Like if it was the Android framework, you'd be doing Java or Kotlin. If it was the Play framework, you're looking at Java, Scala, and so on. So there's a family tree of languages. It's kind of very cluttered, there's a lot of lines there connecting lots of different things. And this is since 1950 to basically in around now. So there's a huge, like probably a lot of languages that are out there. And what we're going to do is delve into 3 particular areas within this family tree that we're interested in, because we're focusing on an object-oriented language in here and languages that have spun out of that. So we're interested in looking at where do those influences come from and how were they born, basically. So one of the clusters that we're interested in looking at is the Lisp Fortran cluster. So that came around in the late 1950s, and it was a major departure from Fortran. And we look at what we mean by major departure in a few minutes. We will discuss some of the characteristics of Lisp. But what we did was we included some quotes here that you can have a look at. Lisp was just, it's known as the Chuck Norris of programming languages. It's the bar other languages are measured against. Knowing Lisp demonstrates developer enlightenment. So Lisp is a main father of all of the languages. So let me see. Sorry, it's just refusing to scroll down on me. Okay, I'm going to have to scroll. It won't let me page down for some reason, lads. Sorry. So basically, we can see here Lisp in the 1958s, and there's Fortran at the top here. So Lisp came after Fortran, and what we're interested in is Java down at this end here. We're interested in this cluster down here that we will explore later on, and the influences that they've had on it and where they came from and so on. So the other one that we're interested in is the Smalltalk cluster. This was basically a pure object-oriented language. Everything was an object, including your ints and so on. They're all languages. Your primitives, the whole lot are all objects. And Smalltalk had a profound influence on some of the languages that are really popular today. Objective-C, a lot of these languages borrowed stuff from Smalltalk. So Objective-C, if anyone has ever used that one, it borrowed concepts from Smalltalk, the syntax and so on. Java, we borrowed bytecode. We'll talk what bytecode is in a week or two. And garbage collection, we'll go into what those are, but Java borrowed those from the Smalltalk language. And Ruby, it's very, very similar to Smalltalk. So even though it was a language from years ago, it has an impact on the clusters that we're looking at the moment. And you can see the Smalltalk cluster here, and you can see the influences on Ruby down at the end, and you can also see influences on Java down at the other end down here. and Oak. Oak was the first predecessor of Java, and it was renamed to Java. So Smalltalk has had an influence on the mainstream object-oriented languages that are out there today. We're interested in this module in looking at Java and Kotlin, some of the languages that have emerged out of Java as well. And they're all the object-oriented languages. So that brings us on to the third cluster within that major cluster that we showed you on a couple of slides ago. So what we're interested in is Java. We will delve deeper into where this went and further on, and the Groovy. We can see a lot of the influences that are coming out here. So we're interested, if we reduce that diagram down, so this is just the cluster itself, but we can't see the influences from the 1950s. So this diagram reduces down what we're interested in. So you can see Fortran and Lisp at the top there, and you can see the influences down here. The grey ones are the newer languages that are emerging out of Java. So what we're interested in, so Java and Scala, the framework that you're going to be looking at, the Play framework, uses both those languages. Java, and you can see it directly, a direct descendant of Java is Kotlin. If you use an Android framework, you can see that Java and Kotlin are very closely related. So I suppose one of the main questions that you're going to be asking is, why are there so many languages out there? You saw the diagram I showed you at the beginning, huge amount of them. And this one particular guy was looking, Kevin Keller was looking at Lisp. And he said that basically one of the main ways to describe why there are so many programming languages out there is to describe them in terms of the problems they fix. So generally languages die and are replaced by other languages based on them falling short somewhere. So if we have a look at this diagram of languages, and we can see Fortran there, I'll go on to a new slide now in a second, but you can see that there is a lot of reasons listed up here as to why certain languages have disappeared. And if we delve deeper into that, we can see here, if we follow down the assembly path, assembly was too low level, so ALGOL came out. Assembly was too low level, so C was born. That was too low level, so C++ was born. That was considered a kludge, too many things all thrown together in it, and not very great to code in certain situations. So Java was born, and so on. Scary syntax, so C# was born. Or sorry, JavaScript was born. Java was controlled by Sun years ago, so then C# was born. So you can see how languages have evolved based on them not fulfilling certain things, and newer languages took their place. If we look at another one of those clusters here, assembly, too low level, so Fortran was born. And then if anyone is coding in COBOL, PL1 or any of those, Fortran had scary syntax, so COBOL was born. And you can see how Python was born as well, because where it came from, assembly, too low level, ALGOL. ALGOL was lacking data types, so Pascal was born. It was too wimpy for systems programming, so Modula and Modula 2 were born. Scary syntax, Python emerged. So you can see how these languages have gone by the wayside, and Python is now the successor. So one of the other things that we'd like to look at as well in this is Lisp. So that was the language that was designed in the 1950s. And this is the language that we said that, kind of being able to program in this is, you've reached developer enlightenment and so on. It was a radical departure from the existing languages that were out there, namely Fortran. And it embodied 9 new ideas, which basically have been classified as a wish list for programming. So what we'll do is we'll have a look at these guys and see what they are. So what we're looking at here is conditionals, a wish list for programming. Anyone know any programming languages that don't have conditionals? Pretty much taken for granted now, but Fortran didn't have them at the time, and Lisp brought them in. Function types. These are, you can have a read through these later and have a look at this link here to give you a lot more detail on them. But function types was another thing. What we have now in Java called lambdas. Recursion, this was in the wish list for Lisp as well. Dynamic typing, we're going to go into dynamic typing and what that means today in these slides. Garbage collection, Java has that. We're going to look at that. Some of the other languages don't. Programs composed of expressions, some of these aren't in in Java. And you'll see that this is what Lisp was giving was a huge amount of functionality. So a symbol type, a notation for code using trees of symbols and constants, and the whole language there the whole time. So no real distinction between read time, compile time, run time, and so on. So this was the main wish list. But if we look at that in the context of Java, Java has conditionals. Since Java 8, Java 9 is being officially released tomorrow. Since Java 8, there's now a function type. They're the lambdas. We will look at lambdas as well at some stage during the course. There's recursion in it. It's not dynamically typed. We're going to delve into the dynamic typing today in this lecture. It is garbage collected. We will cover that in week 2 or 3. We'll look at that with you. It doesn't have, its programs are not composed of expressions. There is symbol types. We'll be covering that throughout the module as well. And it doesn't have any of these guys either. So from the wish list, from what Lisp had in the 1950s, Java is fulfilling 5 of those. But if you look at the languages that have emerged from Java, like Groovy, Ruby, Python, as we were talking about earlier, Kotlin as well, you can see that there's a huge number. They have more items on the wish list in their languages. And they also have meta-programming, a lot of these guys, where you can generate Java code on the fly using annotations and so on. And we'll discuss those with you as we move through the module as well. So you can see, if I just page up again, you'll see that Java has 5 on the wish list, and the later languages have evolved into having more on the wish list than Java has. So what we're interested in, on that wish list, dynamic typing was listed in there. So we're going to look at what does dynamic typing mean. So it's a concept basically of applying a type to a variable. So you've got a typing spectrum here. And what we have is, you have one axis here, strong, weak, and you've got another one, dynamic, static. And languages are often classified based on their approach to this typing. We're going to look at exactly what dynamic and static are and what strong and weak are. So you can see languages like Java that we're going to be looking at it's strongly typed and statically typed. And we'll delve a tiny bit into JavaScript in this lecture, and you can see it's down in the total other area down here. It's dynamic and weak. And we look at what those mean by example. When you're defining these terms, if you have a look around on the internet and start reading books, there is widespread confusion and disagreement about the meanings of these words, those words that are on our axis there, static, dynamic, strong, and weak. So what we have done is define them in the way that we will use them in this lecture here. So we'll look at dynamic and static. So we look at this axis first. And we're going to look at them, as I was saying, in the context of Java and JavaScript. So first off, what do we mean by dynamic typing? So variables, types, declarations are not mandatory, and they will be generated or inferred on the fly by their first use. So we don't have to give them a type. It will be inferred. And if this is a little picture here, there's your code in your dynamic language. You're at compile time. And then you've got your runtime. So different stages of the development process. So dynamic typing is done at runtime, basically. And the type is inferred at that stage. And there's a nice video down here, actually. There's a nice video down here that you can click on the link and you can watch that. Then it gives a nice introduction to typing. So a dynamic typing example from the JavaScript perspective. We can see here that a type is not assigned to these variables here. Var, this means that I can just change the contents of greeting here. And it's also, I've left it as undefined. And then I have var some random integer. There's my variable name. I just put in 100. I didn't give it a type at all. I didn't say it's an integer or whatever it is, or double. And the same here, I gave it a variable name, and there's no type associated with it. So what happens is the JavaScript engine chooses a type it feels best describes the data contained inside of your variable. It assigns it behind the scenes. So there is an assignment of a data type, but it's behind the scenes and it's done kind of at runtime as well. So then static typing on the other end of that spectrum, variable declarations are mandatory before usage. Otherwise, they result in a compile time error. So now instead of the dynamic typing occurred at runtime, we're now looking at static typing occurring at compile time, that it will not even get to runtime if you haven't given it a type. And certain languages adhere to static typing. And that's one that we're going to use, which is Java. So I need to give it a type, string, greeting. So I have my greeting variable, given it its contents here, I've assigned a value, and I have named it, given it a type of string. Same here, an int and a double. Each one of these variables is given a type. So if we don't assign a type, we get an error. So Java is a very statically typed language. Types determine the operations we can perform on the variables as well. So int, if I've got a variable, some random integer, I know that I can do mathematical operations on that because it is a type of an integer. So the operations that I can perform are dictated in Java by the type that you assign them to. So basically, dynamic and static typing is the amount of time check-in enforced by the compiler versus leaving it to runtime. So static is done by the compiler, dynamic is done by runtime. So on the other axis, you've got your strong and you've got your weak typing. And once again, we'll stay within Java and JavaScript as our examples for these guys. So strong typing. So we're moving past variable declaration. So once a variable is declared as a specific data type, it will be bound to that data type. You can explicitly cast the data type though. Okay, so if we look at Java, which is a strongly typed language, and what we've done is a little small screenshot in here. So what we have is int number 1 is assigned 4. That's my static typing. I've given number 1 variable the type of int. I've just created a second variable called number 2 of type int. And then what I have done is I have tried to assign a decimal point into my integer variable. And it's giving me a type mismatch error. It won't even compile. It gives me this error. And I have two quick fixes that I can do. What it's saying to me is you can't convert from double to integer. So I have two quick fixes. One is that I can cast something into an integer, which means I can explicitly drop the decimal point, or I can change the type from being an int into a double. So we'll look at those two fixes for a second. So this is the one with casting. What I have done is my 4.6, I am casting it as an integer and putting it back into an integer variable. This means that I will have a loss of precision and I have dropped my 0.6. So that is, it depends on what you're doing as whether that's acceptable or not. Then you have another example of it. This is the fixing with the type. We change it to the correct type if we don't want the loss of precision. So this is a strongly typed language. So the operations that I'm doing on it after it's been declared are being dictated by the type. So another example here. So what I have done is I have declared a variable A of type integer and given it a value of 4, declared a variable B of type string and given it the string value of 8. Okay, so there's static typing going on within my Java code. And then what I'm doing is I am trying to apply a multiplication operator between an int and a string. It's undefined in Java for those data types. It won't do it. It's a strongly typed language. It refuses because it won't let you do a multiplication on a string and an integer. And that's another second example of strong typing within Java. On the other end of that spectrum, weak typing. So variables are not of a specific data type. However, it doesn't mean that the variables are not bound to a specific data type. So all of that is done in the background. So in weakly typed languages, once a block of memory is associated with an object, it can be reinterpreted as a different type of object. So putting that into code, if we have a look at that, what we have is JavaScript in here. So I just left the top of this part here so you can see where you can actually just code JavaScript. Just look for in a browser, just play around with it and see what happens. It's called Coding Ground. You just Google that and you can see it. And you can try out these guys yourselves and just play around with what's happening with the typing in a weakly typed language, a weak dynamic typed language. So in this case, I have declared A as a variable and I've given it a value of 4. That is dynamic typing. I haven't said what type it is. And the same here, I said I'm declaring a variable B and I'm giving it a little string of 8. So then what I am saying down here is I am going to add 4 and 8 together. Okay, so when I add the two of those guys together, it allows me. Okay, so that's your weak typing there, and you can see that the result here is it gives me 48. Okay, if I give you another example here, what we're doing is we're changing that from being A plus, which you would be able to do that nearly in Java. In this one, we're doing pretty much the exact same thing, except for I'm doing a multiplication. And see what's happened with my result. It has done the multiplication. Everything was the exact same. I'm still dealing with a string 8, and I'm dealing with the number 4. But in the background, it knows what it's supposed to do, and it multiplies them. 4 by 8 is 32. And that's the example of weak typing. I tried that in Java, and it wouldn't let me compile it. That's a strongly typed language. And in this case, here's another example. I've replaced B with just a Boolean value of true. And when I do an A plus B, Boolean true is a number 1, and it adds 1 onto A, so it gives me a value of 5 that we can see here. So that's what weak typing is doing there. It's interpreting what it's going to do with the mathematical operators based on the typing that's there. So strong and weak, how the runtime constrains you from treating objects of different types. So it decides what it's doing in the background with the allocations. So this is the last slide here now on these on this set of notes here, and it's just to show you again the typing spectrum, and where Java is a strong statically typed language, JavaScript on the other side is dynamic and weak. And by all means, try out that coding as well yourselves and have a look and experiment with it. But one of the main things on this is, see the way all of these languages are placed in a specific location. This is to indicate that it's actually a continuum rather than an absolute measure. In this case, Smalltalk is more strongly typed compared to Python, which is more strongly typed to JavaScript. Okay, so you can see that there is, levels of strength and levels of weakness and levels of static and dynamic in your typing spectrum. And we'll be moving on to more to do with typing as we progress through the module. So that is that for that slide deck. So what I'll do is I'll give you another break as well, and I'll put up the poll and we can have a chat then. So poll, I'm going to put up another poll here. So what hands-on experience have you with an object-oriented language? So I leave that poll up there and I'll give you a break for 5 minutes, and then Eamon will be back to do the last slide deck with you. So I'll just reset that timer, put it up for you. So see you in a little bit. We'll be still in the chat rooms to have a chat in the 5 minutes there as well. Thank you.
Okay, guys, it's me again now for a few moments. Hope audio is okay there. I assume you can hear me unless I hear otherwise. Just looking at the poll there, it's kind of consistent with what we've seen so far. Got 7, 8, 9, 10 people that somewhat or quite a bit. We've got 4 people who have considerable and then 3 at very little. So it's similar enough from the previous polls and not unlike the kind of cohort we were expecting on the course itself. I'll take this poll down now and we'll proceed with our last discussion. So we've had a tour through programming paradigms in general. We've looked at some of the major name checks on the major paradigms in the history of computing. We've explored the evolution of programming languages, particularly looking at the programming language trees and how they influence each other. And particularly we're interested in the evolution of our understanding of typing and type systems over the years. We've also had a walk through software engineering knowledge, as we called it, from programming languages to data structures, to patterns, to architectures, components, frameworks. And bear in mind, this is a general overall tour of the field, not really the subject of our course to delve in more depth to many of these topics, but just to give you a mindset from which we'll start to make some progress on the subset of the field that we're exploring. We'd like to finish off with some code. Again, if you're new to Java, don't be too worried. We're not expecting you to understand this all immediately. Just trying to get a general flavor of modern programming languages, and particularly about what we can see as evidence of some convergence taking place, particularly in the languages Swift, Kotlin, and Groovy, and how all of these relate back to Java, which is the vernacular language we're exploring in this course. So I'm going to look at this program here. Now, don't be frightened by this. It's a fairly simple algorithm, in fact. And we're going to look at this for about 10 minutes, various versions of this program. It's a little application to filter a list of strings. That is, to create a list of strings and find out which strings are less than a given number, 3, and then just print out those names. So in this example here I'm creating the list and I'm initializing it. So I now have a list of 4 strings. I then make a call to a function to perform the filtering for me. This is taking place here. And this function call is invoking, we can see this method here. And this method is proceeding through a fairly standard for loop, going through the array of strings and adding any string that's less than the given length. The given length is passed as the number 3 in this instance. So 3 is passed here, and that's the length we're going to be comparing against here. It's Java. It's quite verbose. When you think of what it's being asked to do, it's quite long. It's probably a little bit contrived, but it's not unusual for a style of programming maybe 10 years ago or 15 years ago. Particularly when Java first arrived, this was probably the only way you could do it. Let's have a look at alternative versions. First of all, Groovy. Groovy is a very influential language. Rose about 10 years ago as a Java compatible language, and one of its key features was that a Groovy program was also a Java program was also a valid Groovy program. So there was full compatibility between Groovy and Java. So we could take a Java program, land it into a Groovy environment, and it would just work as was. There's no change here in this slide. However, Groovy proposed a range of simplifications from its perspective. They de-emphasized generics. We haven't discussed generics yet, but don't worry about it. They took out some syntactic noise like semicolons, and also removed some other perhaps unnecessary boilerplate from Java programs, such as importing standard libraries. And here's another version of the same program. It's still exactly the same as more or less the Java version. We are still creating a list here, calling a method here to filter the list. And then the method itself, you can see at the bottom, is more or less the same as the very first version we had. However, Groovy kept going with the innovations, and they were looking at removing aspects of Java, particularly the requirement that all methods had to belong to classes. And once that small tweaks were made, we can simplify the program further. We can promote the algorithm to being just a function, not bound to any class, just a filter function. And we can express our driver for the algorithm as a script, really, without belonging to any class or function. Still looks reasonably similar, though, to our first attempt. And let's look at some other simplifications. In particular, Groovy proposed that because lists and data structures in general are so common, we should promote manipulation of those data structures into the notation for the language itself. And we should also incorporate specialized functions for manipulating data structures, because that's such a common aspect of our day-to-day jobs. This produces a dramatic shift in the same program. Here we're looking at a string or a list literal here, creating a list of strings just in one line. And also we're looking at another major innovation here, a filter function already available in our library and accessible via a special notation called a closure. In fact, we can simplify this algorithm further down to just these 5 lines. Create the list, which is here. Print out the list. Filter the list. Print out the size of the shortened list, and print out the contents of the shortened list. And in particular, the way we're filtering the list implemented a fairly radical departure over Java. Namely, the passing to a function an algorithm. And the algorithm is encapsulated in this construct here, starting with that brace and ending with that brace. Between those 2 braces is the condition to perform the filtering. And in fact, between those 2 braces, I could have any algorithm I choose. We're passing what Java now calls a lambda, or what other languages call closures, to a function. Same program though. It's a JVM compatible language, so the program written in the Groovy notation can subsist alongside the Java programs. And they can use the same language environments, they can use the same IDE, they can use the same libraries. In fact, the names list is still an array list, and it's still the same array list data structure as is embodied in the Java program. That's a dramatic reduction there in the verbosity of what would have been a very traditional way of programming this maybe 10 years ago. There are other languages, though, that are also following a similar track laid down by Groovy. I'd like to take 2 more short examples before we finish up in that context. Particularly, we're interested in how languages approach typing, not by focusing on dynamic or weak typing, but via a type of type system known as type inference. And type inference is becoming a central feature of many programming languages that are strongly typed. And it's also being introduced gradually into Java itself. And the notion of type inference is that we can expect the compiler to get involved in figuring out the type at compile time. This reduces the amount of type information we have to provide, and the compiler should have enough information in many environments, in many contexts, to make the correct type decision. Let's take an example. Here's our Java program again. It's exactly the same one we started with originally, filter a list of names. Here's a Swift version of the same thing. Now, Swift is a strongly typed language. It's not dynamically typed like Groovy. In fact, you can see Swift is influenced by, you might say, Java. Swift would say its influences are earlier, back to C++ and Python, and also functional languages. But there's a common look and feel to these languages. And you can, if you know Java, you can read this language, this example reasonably easily. However, Swift is on its own journey in simplifying and reducing boilerplate code. Swift implements type inference, which means when we declare a variable, we don't have to specify the type as we introduce the variable. We can just use the keyword var. You've seen that in some of Siobhan's examples. Var is a neutral keyword. It means introduce a read-write variable. And we specify the type just once, not twice, as you can see in this example on the left and on the right. Now, Swift has other innovations which are quite strikingly familiar. We have list literals that are exactly the same as Groovy, in fact. In fact, both of those are influenced by Python. We have closures. Again, the syntax is startlingly similar to the way Groovy has defined how we can customize an algorithm by providing another algorithm to a function. And also we have script. That is, we can take Swift programs out and capture them as simple statements to be run independently of any class. So this same Java program converted to Groovy, which is dynamically typed, now also converted to Swift, which is strongly typed, but uses type inference to reduce boilerplate and verbosity. Okay, we could stop at that example, but I'll just do one more example because the convergence here is interesting to look at and contemplate in a general sense. This is Kotlin. Kotlin was recently announced as the fully supported language on Android. So you could think of Swift and Kotlin as the two major languages supporting application development on the iOS and mobile Android mobile platforms. And it's interesting to look at how those languages take a common approach to a variety of key features. Previously, they were quite divergent, as Android was Java-based and iOS was Objective-C. Those languages were quite distant from each other. But these two languages have grown quite close. Let's look at a progression of this Kotlin program into something a bit more succinct. First of all, we can dispense with the need for a class. So we just have two functions. Secondly, we can employ closures again, or we call them lambdas or function parameters in Kotlin. You're seeing a pattern here that we've seen already. And we can reduce the entire program to a simple function. And in fact, we can reduce it down further to a short script. Let's look at this for a second. We've got the declaration of a list in place. It's a mutable list, that is, it can be modified. And we're initializing the list immediately. We're printing out the elements. We're then performing a filter on the elements, and we are making available a reduced list based around a condition we're supplying to this closure. And finally, we're printing it out. So back to our introductory example, the three variations here, Groovy, Swift, and Kotlin are startlingly aligned, particularly Swift and Kotlin, because both of those languages are strongly typed but using type inference. In other words, the compiler is involved in making sure you are composing a correctly formed program. And yet those programs, those scripts exhibit many of the aspects of dynamic programs, which is the Groovy paradigm. So there's hope for us yet, whether we're developing on Android or on iOS, the two major platforms. The concepts we need to grapple with and the paradigms we can use are coming into alignment. This is obviously attractive from a programmer's perspective. It means our skills can be improved and spread across multiple domains. Okay, thanks for your attention. That's our chat this morning. This afternoon, sorry, this evening for those of you elsewhere. We're delighted that you've joined us for the course, and we're looking forward to the next 12 weeks. We've toured the labs now already, so you should be familiar with where to go. I see a lot of you are joining the Gitter chat room, which is useful. Just draw your attention to the lab again here. This is the practical part of this week's work. Series of steps you go through. You'll be downloading, installing an IDE we're going to use, and you'll be introducing a simple program that we're going to experiment with further next week. The application you build is also made available here, and you can download the completed application, if you like, as a zip file to compare it with what your solution has worked out like. Thanks for your attention again. We're going to hang around until 7 on both chat rooms, so feel free to contact us. If you're in the Gitter room, you can private message us. If you're in the Adobe Connect room, you can also private message us, so we can chat in either domain. We look forward to chatting to you during the lab session as scheduled, and we'll be back again next week for our next session. Okay, thanks again, and talk to you soon.